In this video, we are going to talk about an important parameter associated with the MOSFETs. Before we can talk about the voltage and current characteristics of NMOS device, well, this parameter is known as the threshold voltage. Okay, so the threshold voltage of an N-channel MOSFET, which is shown in this figure 7. You see, you need a minimum voltage level, a minimum gate voltage level, such as to create a channel for the conduction of current from drain to source. Okay, so this threshold voltage is defined as the applied gate voltage that is needed to create an inversion charge in which the density is equal to the concentration of majority carrier in the semiconductor substrate. Okay, so the idea is as follows. This is a p-type substrate. Okay, so this is your p-type substrate which has a majority of holes. Okay, positive holes in it, and then you have those two n-doped regions for drain and source. Then gate is insulated by an insulator, silicon dioxide, or it could be some other form of insulator. So it is separated. It's like a MOS capacitor. Now, what happens is, for example, if you don't have any gate voltage, okay, so let's say if your VGS is with respect to the substrate. So you see this connection is from the substrate body, and this is the source. Okay, both are short circuited and connected to the ground. Okay, so let's say to start with, if VGS is open circuited or 0 volts, then that means you're not creating any channel. Okay, the gate is not controlling the conductance of the semiconductor material. There is no channel. Okay, the both drain and source are separated by the p-type substrate, and there could be no conduction. Okay, even if you are going to increase the drain voltage, if you're going to increase VDS, well, what you are doing is there is a PN junction. You see over here, there is a PN junction. You increase VDS, basically you're reverse biasing this more and more. So the depletion width is increasing over here. Okay, you can't do anything with the source terminal that's grounded, but the depletion width is increasing. So basically nothing is going on unless you don't change or don't increase the gate voltage. Okay, so for a given NMOS or p-type substrate MOSFET, what you do is you connect this to VGS supplied battery. Okay, this is also ground. So this is my gate voltage. Okay, and this gate voltage is it has to be a positive gate voltage, and if I go on increasing this gate voltage, well, what happens is an electric field, establishment of an electric field. So the metal plate gets the positive charge. Okay, so metal plate has a positive charge, and then if you recall, what happened previously was that you will end up having a space charged region, a space free charge region, which is the depletion region, and which is going to have the negative charge carrier. So the bottom plate of this MOS capacitor, this is your MOS capacitor, will have negative charge. Okay, and the holes are going to accumulate somewhere at the bottom of the substrate. Okay, so due to the electric field, due to the energy present over here, these holes, these atoms are going to lose electrons, and these electrons are going to be attracted at the metal and the semiconductor interface. Okay, so this electric field direction is as such, which is established inside the dielectrics. It's a capacitor. Okay, so the thing is that you need a positive gate voltage in order to create. You need a certain positive gate voltage to create channel, and this VGS greater than VDN is a threshold. Okay, which ensures that there is a channel. Okay, although the source and the drain terminals are reverse biased. These junctions are reverse biased. You can see that this is N doped. Okay, this is P doped. So there is a depletion region that already exists. But in order to have conduction of current from drain to source, you need a channel. So for that channel, that VGS needs to be positive and greater than the threshold voltage. This threshold voltage is the minimum voltage that is required to turn on the transistors, so the transistor conducts. Okay, so that's the idea. This is a parameter associated with important parameter associated with the transistor. So okay, for this n-channel enhancement mode MOSFET, I think I explained this earlier. If you go and watch the earlier videos, you see this in the part 2 of MOSFET. This enhancement mode means that you need to apply a biasing. Okay, you need to apply a biasing to create the channel. If it is a depletion mode, then the channel is fabricated. Okay, it's already fabricated. It already exists. So you can even connect your gate terminal with the source terminal, and both can be grounded. So for enhancement mode, you need to have a positive for this NMOS MOSFET. You need to have a positive gate voltage, okay, and it should be at least the threshold voltage, to create enough charges in the channel which can ensure the conduction of current given the application of the drain voltage VDS. Okay, S is basically at ground, so this is ground. This is, you can see over here. Okay, S is 0. So for n-channel enhancement mode MOSFET, the threshold voltage is positive because the positive gate voltage is required to create the inversion charge or the channel. Okay, so inversion charge or channel is the same thing. This is adjacent to your oxide and semiconductor interface. Okay, so if the gate voltage is less than the threshold voltage, the current in the device is essentially 0. So that means the transistor is off. It's not conducting. So this condition is when the transistor is off. Okay, so this condition implies that your gate voltage, since we are adding this with respect to S, source terminal is grounded, substrate is grounded as well. So this, when VGS is less than VDN, the transistor is simply off. Okay, otherwise it's on. So if the gate voltage is greater than threshold voltage, well, the drain to source current is generated as drain to source voltage is applied. Okay, so the gate and drain voltages are measured with respect to the source. Okay, which we are doing for now, because this VGS, VDS, everything is with respect to the ground. So this is your drain supply, right? As you're going to increase the drain, well, you're going to increase this depletion bits as well. Unless you don't have a channel, well, there is no current flow from drain to source. So the transistor is off. Okay, so in this condition, the transistor is off. Okay, so there is no depletion rates. The transistor is off, given the condition that VGS is less than VDN. In this condition, it becomes on, and you can see that you have a depletion region or a channel that connects both the drain to source. Okay. All right. Now this is the same thing. Basically, what it shows is okay. So repetition of figure 7. So it shows n-channel, again n-channel enhancement mode MOSFET with source and substrate terminals. Source. So your source and substrate body is connected to the ground over here. So the voltage is less than threshold, and there is a small drain to source voltage. Well, this is actually the leakage. If there is any current, there could be a leakage current due to the minority carriers, but it's not significant. Okay, so if your gate source voltage is less than threshold voltage, there's a small and there's a small drain to source. There could be a leakage current, but it's not significant. So, but if you need to turn on the MOSFET, you need the gate voltage greater than the threshold voltage. Okay. So with this bias configuration, there is no electron inversion layer. The drain to source, the drain to substrate PN junction is reverse biased. Okay, you can see that this is N doped. Okay, and this is P doped. So this is your reversed PN junction over here. You have a reverse PN junction over here. The substrate is P-type. This is N-type. Okay, so this is reverse biased. So you can. The thing is, you cannot have the charges flow through the substrate towards the source. Well, you can't have that. Okay, because the junctions are reverse biased. The junction over here is reverse biased. The junction at the drain side, at the source side, both are reverse biased. So 7b shows the same MOSFET with an applied gate voltage which is greater than the threshold voltage. In this situation, an electron inversion layer is created. Okay, so if this condition is satisfied, you have the channel over here, and this channel is responsible for the conduction, the flow of charges. And these charges, again, these charges are, since this is NMOS, we're talking of NMOS, the channel will consist of negative charges or electrons. So when a small drain voltage is applied, the electrons in the inversion layer flow from the source to the positive drain terminal. And if you recall, the conventional current is the other way around. It enters the drain terminal and leaves the source terminals. Okay, so note that the positive drain voltage creates a reverse biased drain to substrate PN junction. So current flows through the channel region, okay, and not through the PN junction. So we don't have any current conduction through the substrate. Okay, this is not the path. This is the path of the current flow. All right, now, well, this figure summarizes the entire story of the threshold voltage. You see, if your gate to substrate voltage is less than VDN, the transistor is off. Okay, by off I mean the ID is 0 over here. Okay, it means the drain current, which is flowing from drain to source, if you consider the conventional mode of current transfer. Well, that's 0. Okay, so but as you are increasing the gate voltage, you start creating the depletion region like this. Okay, over here, the current starts to flow given you have a VDS. Okay, you have a VDS, but you see that for these two curves, one is in the pink and another the dotted curve, the dashed curve. For the given VDS, I have more ID for the given VGS2. Okay, so let's call this ID2. Why is that? Because as you're increasing the you go on increasing the gate voltage, what you are doing is you are increasing this this channel width. Okay, channel width is increasing, so this channel width goes like this, and you have more and more space. Basically, thing is like this. You have more. The channel width is increasing. The channel width increases as your VGS increases. Okay, it becomes large. You have more and more channel width. That means you have more density of charge carriers that that is responsible for the flow of current from drain to source. So more charge density turns results in more conduction of current from drain to source. So it says over here, with the larger gate voltage, okay, so what happens over here is if the gate voltage is large, the VGS2 is larger than VGS1, you have more current. Okay, the larger inversion charge density is created, and the drain current is greater than for the given value of VDS. Okay, so when VGS greater than basically VDN, which is the threshold, channel inversion charge is formed, and the drain current increases with VDS. So as you're increasing the VDS, well, yes, you are increasing the drain current as well. Okay, but there's another parameter to see, that is your VGS. VGS controls the since you're increasing the electric field in the MOS capacitor, so you're increasing the charge density. Okay, so with that you get more drain to source current. So this is a plot of ID versus VDS characteristic for small values of VDS at 3 different VGS voltages. Okay, so in these conditions your transistor is on, so the other two curves the transistor is on, so that ID is positive and non-negative. Okay.